Okay, thank you for the introduction. I have planned to speak about a few things. This is some recent work that we have done. It's good to have the DRAM background to start with. The placement of this kind of work would be somewhere just before we go off the processor into the DRAM. So the sort of work that I'll be talking about fits into what is called a last level cache, or even some of the earlier levels of the cache, still within the overall ambit of what is understood to be the memory system and the memory hierarchy, but at least this particular work or a couple that I'll be talking about does not go into the DRAM. We need to be aware of what's happening elsewhere in the DRAM and try to anticipate that. But the optimizations that we'll speak of are at the cache level, not at the DRAM level. However, these things don't work by themselves. Memory is organized in several layers as a hierarchy, and they need to coordinate. These different layers need to coordinate with each other in some way. Of course, they need to be aware of what is there before and what is there later. Okay. Before we go into detail, let me just outline a little bit about what we are up to. There are several dimensions of primarily memory, but you can think of these in very different ways. I am just overall calling this the Embedded Systems Research Group, but I'll illustrate with a simple example the idea of Scratchpad memory. Some of these occur in the context of embedded systems. We understood a little bit about the server system, which really falls into what you would call a general purpose computing. Embedded systems refers to a little bit more application specific, more constrained with respect to the resources, with respect to the power that is available. So in some ways it could be the other extreme of the computing space. If the server and data center, these are at one extreme, the embedded systems might be at the other extreme, where you want to compute, you want to do a lot of things, but with very small amount of resources, small amount of power, and so on. Of course, you know that we are moving towards a world where these things interoperate. Both of these are there, right? You have these high-end servers and data centers and all of these doing all the processing in the back end, but in fact the interaction with the human being, interaction with the environment might be happening with tiny devices that are embedded systems. So in some ways there is a very nice coordination among all of these different levels, which of course provides the researcher very nice opportunities for investigating the different modern problems that come up with respect to computing, with respect to storage, with respect to management of data, and so on. So we had done some early work there, followed by, that's one example that I'll be talking about. There is some work on this on the cache management in general. These architectures are evolving very fast. Therefore, there are a lot of opportunities for managing these memory architectures, whatever the level of the memory hierarchy we are talking about. Lots of changes, and because there are changes, there is the need for the system architect, for the OS designer, for the compiler designer, for the application writer, all the way all along the computing stack. When the memory architectures evolve, when they change, a number of new opportunities arise with respect to how do you properly exploit the newer technologies that are there. So they influence everything. But in addition, so these are the two things that we will take a look at in some more detail, but in addition to that, some of the other things that we are looking at, first we have spent some time on the idea of post-silicon validation. It's a very interesting new area where you build very specific design for debug structures when you design any complex system. This is not new in industry. Industry has been doing this for some time. This isn't properly formalized in academics. For example, it's hard to find a textbook that will tell you in a very nice way what these validation structures are look like, what do they look like. But they are actually very fundamental. A lot of effort in modern processor design or any high-end system design goes into building these validation structures so that once you get some sample chips, you are able to debug the design in some way. This isn't a trivial structure. You don't have that much visibility into a processor. You have only some few hundred pins or something like that. That's not enough to figure out what is there in this particular cache line, what is there in some particular register. There is some reasonable connectivity, some reasonable external interface, but a lot of effort goes into building structures that would enable validation. Okay, there is one level of validation that we already do when we simulate a design. We design, so this is all in software, right? You build a model of the design and you do a software simulation, which has inherent difficulties with respect to scale. If the design is very large, then the simulations will take months and years and so on. So you do need more sophisticated mechanisms to validate complex designs after they are fabricated, not necessarily in volume production. By then it may be too late, but you may go through an intermediate stage where you get some samples in a lab but put them to very extensive testing, and in the process you try to investigate what has gone wrong, why it has gone wrong, and so on. You need a lot of such support. So anyway, as a research topic, not much work exists. This is still a relatively recent idea. Therefore, it hasn't received the kind of formal study that, for example, a processor pipeline has received. You understand that even though modern processors are very, very different from each other, commercial implementations are very different with respect to how many pipeline stages are there, with respect to a number of details. A theory certainly has emerged with respect to how to treat it conceptually without necessarily worrying about specific details. There may be an opportunity eventually to talk about validation structures in such a way. But anyway, there is some effort that we have spent on this through some of these. Almost all of these have some kind of industry collaboration or the other. But in addition to these, I will not specifically talk about these, and the introduction to that we already got. In fact, the thermal issues that come up when you have 3D memories were problems that were pointed out to us by Saravanan from IBM. We haven't reached a stage where we have solutions, but nevertheless we have tried to, in the recent past, build some open source based infrastructure where in a system simulation where there is a processor, there is a 3D stacked memory, there is some application, we are at least able to observe some of the effects that were pointed out, the thermal effects that were pointed out. They're very interesting. Electrically, of course, it's interesting. What to do about it once those effects are there? You would like to minimize them so that you don't need to repeatedly throttle your systems because they are getting too hot. If they get too hot, then you pretty much need to shut down things or just wait until it cools down or provide paths for cooling down. You are wasting time, you are wasting energy when heating up happens in the processor, in the memory, everywhere. But what to do about it? Once knowing that such a phenomenon exists in the 3D memory, for a system architect, it presents some very interesting problems. Can we control the system in such a way that we minimize the effect? Well, we don't have results on this yet, but we are in the phase where we have tried to build some infrastructure based on open source platforms, where at least we are able to observe the effect. What to do about it will probably come later. There are a few other topics that I will not go into, not very relevant to today's talk. But that's what the group is doing. 5 to 6 PhD students actually looks impressive, but it's just relatively recent. The growth is relatively recent. So it isn't as though the commensurate amount of work is coming out, because this is students are still in the first year or so. But nevertheless, some progress is being made. Like I said, on that topic there, results are not there, but we are spending a lot of time in the early stage of infrastructure building. Okay, before I go into the main topic, let me give an intuition into this idea of Scratchpad memory that occurs in embedded system. At least initially it occurred in embedded system. Just to give you a view of the memory hierarchy and the treatment of the memory hierarchy that might be very different in embedded systems. These systems are simpler. Simpler does not necessarily mean easier. You have very nice challenges there too. How to maximize computation within a power constrained environment is a very important challenge. We know that our phones are sophisticated computers, right? They occur, they work under very tight power constraints. We, as a user, we demand more and more performance, but on the other hand, to the designer of that whole system, we specify a very tight power budget, nothing more than 3 watts or whatever that number is. So those are very interesting problems, but I just picked a couple of these in the context of Scratchpad memory, just to indicate a different view that we might not have seen earlier in our normal study of memory hierarchy, where we would have seen that picture of a processor pipeline followed by a level 1 cache instruction and data, L2 cache, L3 cache, L4 cache, L10, whatever they are, and then there are all these levels of main memory. You saw in that picture that Saravanan pointed out that even that main memory, there is a tiered structure. Among the different architectures that were shown, if you have non-volatile memory and DDR together, it's possible that there too there is a hierarchy. So it is a very deep hierarchy. But a little bit of digression, I'll just try to motivate and then follow it up with a little more complex example. The Scratchpad memory refers to compiler controlled memory, as opposed to caches which are hardware controlled. What is the difference? Do you understand how caches work? So what do we mean when we say hardware controlled? Somehow what data is there in a particular cache line is not something that you can deterministically point out. You don't know. The point of a cache miss is that once in a while the data that you are looking for does not exist in that cache. You have to look in the next level of the cache. Why don't you know? Who is this you I am talking about? It is the programmer, right? Or the compiler, or statically it is hard to predict what data is there, because the management, the replacement policy and so on, all of that in the interest of time is done in hardware. Okay, we are not exactly aware as the programmer. When you write an instruction and you load a piece of data, you don't know that data is there in the L1 or in the L2 or so on. The systems are architected in a way that generally you expect good performance. Most of the time you expect cache hits, whatever the level of the cache. So that is a hardware control. It is done independent of the code that we write, and when we have memory access instructions in our code, it is actually very difficult to predict at which level of the memory will our request get served. The other extreme could be that you control everything in software. When you write something into a particular memory location, that data stays there until you yourself overwrite it or throw it out into the next level of the memory. It's conceptually possible to think of such a system, right? You throw out all those replacement policies that we understand, but you still have that memory hierarchy. But then in software, you say that this data stays here, that data stays here, and so on. You manage everything in software. That's conceptually possible. That could be the other extreme. Is it a feasible thing to do? While we can give a theoretical argument that you could do it, what's the problem in doing it? It takes too much time. The point of doing it in hardware is that you issue the instruction, this is a load instruction, and the hardware does that searching for us. The search could be an expensive operation, but because of the way it is architected, most of the times there is an element of parallelism that is there in the search. If you have a 4-way associative cache, it means that we are searching in 4 different cache banks simultaneously. Okay, and that search is very, very efficient the way it is done in a cache. If I were to do all of that management in software, this is happening in a way that is, there's a lot of parallelism. While we are doing the memory access, we are able to execute other instructions and so on. There is a latency, but that latency is smartly covered in some way. If I were to do some management with every load, because first of all I have to find when I have a load which of these memory hierarchy layers it resides in, it would waste time. That's the reason it would be difficult to do it in software. In theory, you could write an algorithm that could actually perform better than the hardware replacement algorithms. The disadvantage there is that in the hardware replacement is that the algorithms are very, very simple. You don't have too much time to do a sophisticated search, so it has to be reasonably simple. In software, if you had a lot of time, you could actually do much better if the option was there. But that option is often not there. Not in a general purpose computing system, although these are evolving these days also. But these embedded systems present a slightly different opportunity. What's that opportunity? In that the system that you are building is perhaps application specific in some way. Okay, what do you mean? That embedded, you already know what is that application that's being designed. This is not a server system where you have no idea. You may have some idea about the class of the application, but you might not know what's the program that is going to run. You have to design those systems in a way that the average performance over a large bunch of applications is good. That's the requirement. Here the requirement can be very different. This is a specific device that you are building. It is going to perform one function or a small number of functions that are already known. In that case, we can optimize the system in a much more aggressive way. This doesn't have to be good on an average over a large number of benchmark applications. No, because this is one application. Each application has a different behavior, right? You could exploit that behavior in some way, and so that's just the background of where some of the efficiencies might come from. You could come up with, finally, you could architect a system that is very good for that application, not necessarily good in terms of average performance. So that's the context. Let's look at a variation of the memory hierarchy in the following way. My addressable memory is this. Its implementation is different. So maybe all of this is DRAM, what that off-chip memory is. This represents a standard on-chip memory hierarchy consisting of levels of caches. But a part of the memory space is actually directly accessible to us from the CPU. These numbers are not very important, but the relative numbers are important. As you go off into the further levels from the processor pipeline, the latency keeps increasing. Right? So the idea is, part of the memory space, let us keep close to the CPU at the same level that our first level cache is, perhaps, or the second level cache, or something like that. Yeah. As of now, this isn't for a single application. But these kind of structures came up first historically in the context of embedded systems. The standard general purpose Intel or IBM kind of architectures wouldn't have these features. I will get to a more complex example there, in fact, which was an IBM product and a sort of a closer to a high-end design, but I'll get there. But nevertheless, the historical evolution is that this kind of a non-standard structure came up in the embedded system context. There is nothing application specific as of now here, but I will get to the application specific part of the argument later. This is still a general purpose architecture as of now. What we have done is we have divided the memory space in such a way that this space is treated differently. This is the standard view, but that other space is treated somewhat differently. Even though this is the addressable memory, this part is actually physically close to us, so that in some sense it is as fast to access this memory as it is to access the data cache. Maybe they are of similar capacities too. The data cache, of course, is abstracted. Maybe it's just the first level cache, L1 data cache. Although I'm talking about data cache, you could also argue in terms of instructions. But point of putting it there and not getting that data on the chip through the standard memory hierarchy is that you can control it in software. Okay, now if you write some data here, nobody is going to throw it out. Hardware is not, the hardware controller is not through its policy going to throw out the data to the next level of the cache because it isn't subject to those rules. Okay, but it is subject to a different set of rules. The compiler now has to know, or whoever is controlling it by software, either we mean that the programmer has to make those decisions or a compiler has to make those decisions of what data is going to be there. But there is the advantage that if data is here, if you have written data there, that data is going to be there as long as you haven't changed that decision, you haven't moved somewhere else or overwritten that data with something else. It presents some very interesting possibilities. You could analyze an application and try to figure out which data should go where. That's the first problem that shows up. We had taken a look at problems of this nature, but you could argue in different ways. Let me just put up a simple example. This is a doubly nested loop structure in which we are reading what is a large array, right? This is like a pixel value is being read of a large image, and we are just forming some histogram kind of thing based on the pixel value that was read. We're trying to keep track. In this other array, we are trying to keep track of maybe how many pixels are there with that value. That's all. It's a simple loop. Keeping that architecture in mind, that there is a part of the memory that is available to us to control manually, that is through a compiler and software. But there is that other part that is the standard cache hierarchy. Can we make a decision which should go where? First of all, that on-chip Scratchpad memory might be limited in its size. Large data might not actually fit in there. That doesn't mean you can't make use of it. You would have to actively manage that data. Bring in data, perform some computation on it and throw it out, and then bring some other piece of data. You have to do it explicitly. What the cache was doing implicitly for us, we weren't worrying about where the data currently is, assuming that the cache is going to do a good job for us. Here, if I say that I'm going to put it in the Scratchpad memory, I have to manage everything. So let's just put that out for now, arguing that that is too big for now, we are not going to explicitly manage it. But look at that other one. This is a small array. This could be a possibility. If I have size restrictions on the Scratchpad memory, I could actually store this one into my SPM. This is it's a tiny example put up just for illustration of the concept. But other argument is this is a fairly regular axis ij, and I have a nicely behaved loop, tells us that we know actually almost everything about the way we are going to stride through the memory space as we go through the different loop iteration. This is a well behaved array axis. The other one might not be so well behaved here. Why? Yeah, the access pattern through that array is already known, right? If you look at the way I and j behave, you know how that axis is going to behave for all the axes. It's all very deterministically known, and you already know that caches are designed to take advantage of the spatial locality that is obviously present in accesses like that. The other one is not so sure. What is this locality that you can expect through expect in that other array, that histogram array? I don't know, it depends on the value of level that you are reading, right? If it may happen that the whole picture is a blank image or something, all the pixels are white, and you are actually going to that same location again and again, and everything is fine. It could also be that we are all over the space, but there is nothing to be statically said about the access pattern there. So we are just pointing out that you could use arguments like this to make a decision of what data should go into a Scratchpad memory versus what data should be accessed through a standard cache hierarchy. A good example of a commercial implementation of ideas like that was the IBM cell processor. This is still a little old, but in a research context, even some of the modern processors, not necessarily the mainstream commercial processors, but we see variations of this being tried out for a number of reasons. Most important being there is this nice trade-off between a software managed memory and a completely hardware managed memory. That argument that we went through is a software management. So somehow a compiler has to make that decision. You could put some intelligence there about which way it should go. What is the advantage? Why is this interesting? It would do well if you are able to do a good job of that management. If the compiler is, if there is enough information, we are able to derive that. Maybe with a little bit of help from the programmer, we could actually do a good job of that management. If you can't do a good job, then yeah, maybe might as well just use the hardware cache structure. But there are some powerful advantages. Keeping it software managed means that there is this power overhead that our replacement policies search and replace. There is a searching that is happening, right? When you find out is there a cache hit or a cache miss, there is an implicit search, associative search that is happening in the cache that tends to consume power. How much power? Might be anywhere from 10 to 20, 25% of the cache power could actually be attributed to this tag lookup and the associated control. It's expensive. But if you do it in software, if the management is in software, then indeed the compilation time perhaps increases. Compilation phase becomes more complex, but at runtime, if we have done a good job of the management in software, then you avoid the search, right? The lookup to find out whether your data is there or not in the cache is an expensive process. It is optimized in a way that the latency is nice, it is mostly hidden, but the energy related overhead cannot be got away from, not easily. Okay. So compiler managed memories do present this advantage that if you do a good job, compiler or software managed memories, if you do a good job of anticipating those decisions, then this could be a low power solution. because you have done a lot of the work that would normally happen in caches offline at the time that you compile the code. I am talking about a compiler. It could also be that a programmer is actually making those decisions. So somehow that address space is explicitly made available to the programmer or to the compiler, so that you can decide that this data is going there and that other data is going over there. So anyway, that's the context. This, so I would say, is an example of something that comes close to this compilers managed, software managed memory idea. The cell processor is one. Among the GPUs, this idea has been exploited. That Fermi and the others in that NVIDIA class of GPUs, if you look at their memory, that local data memory is a configurable memory. That's a very interesting concept. There's that much of memory space, and in fact at runtime you can say that I will divide that memory space in the following way. That part of it, first part, you saw the picture that we had put up, that part is going to be software managed. I'm going to decide how to manage that data, but that other part can be treated as a cache. Okay, so that hardware hook is already there. It is a matter of us deciding, the programmer or whoever is compiling, deciding this is the way in which I am going to be using the memory that's there. This is an extension of the original Scratchpad memory idea. It's a kind of extension where dynamic can actually change. You can say that this much for this phase of my program, this phase of my application, this is what the partition is going to be. For that other phase, maybe I will change the partitions. Powerful idea. Okay, if you how would you actually implement such a thing? It's conceptually it's nice to have. Why? Because our application phases present different kinds of memory access behavior. In one loop, maybe I have a certain kind of behavior. In a different loop, I may have a different kind of behavior. Maybe I want to adjust my memory hierarchy the way it is presented to the programmer as I move from loop to loop. It would be nice if such a feature is there. There is the challenge of actually architecting such a feature efficiently so that you don't waste time, you don't waste power and so on, but it's good if such a flexibility is there. But in fact such things are there in certainly in modern GPUs it is there. But getting back to this is the context in which our work was done. So this is actually not caches, these Scratchpad memories that are there with every processor here. These are these workhorses, the DSP engines that are there. They do all the work there. These memories essentially were software managed, and there is this flexibility that that much is a normal memory, that's a Scratchpad memory, but the remaining part is a cache. But what do you do? How do you actually obtain a cache when a cache is actually not there? In the hardware it isn't there, but you could emulate that in software. Again, just an idea. How do you emulate a cache in software? All of these things that we would be doing in hardware, right? The tag, check and comparison and all of those, they could be emulated in everything could be emulated in software. Cache simulators do that all the time. We could do that in the following way. That's just what the picture of that local memory is, but I can say that this much of it is a software cache, and that other part is the Scratchpad memory. This was the model presented to the programmer if we wanted to use it. What does it mean? The cache has data, but it also has, of course the cache has tags, right? But remember, this isn't a cache. We are just emulating that cache in software. Therefore the tag also, I have to reserve a part of my space, memory space for the tags. Now how do I manage this system? That address comes in. I need to, so let's say it's targeted for the software cache. How do you manage this? You would do it in the same way that we would that the hardware cache would manage it anyway. So it would first look up that tag structure to find whether the data is there or not. okay, just like we do it in a normal cache. Fine. We find out that the data is actually there, and maybe it's somewhere here. Essentially, how do you do that lookup? You do it in a way that is analogous, but maybe it's a 4-way cache, and so you read all of these 4 guys, and maybe you do all the 4 comparisons of the tags, and decide that okay, this is there or not there. But it's just that the interface to the memory is just a simple interface. You are just getting data. So first we have to get the one tag line from there. Maybe there are 4 tag values. Then we compare that tag part with all of these 4 simultaneously. Fortunately, that support is there in what is a single instruction multiple data support, right? Yeah. So for ALU operations you are able to do simultaneously, just so that this process doesn't become too inefficient. We'll compare on the efficiency of this process a little later, but this is one part we can do. After that, one of these comparisons will succeed. If it's a cache hit, all 4 will not. These are like 4 different tags. So if it is present, then one of them will succeed. We get back here, and that will tell us where in this data space our cache line is located, and the final step will read that data out. This is indeed what happens conceptually in a cache, but if the cache structure is not there, I have to emulate all of this. You can think of this as 5 different steps. All of this takes time. In fact, the way the system is designed, it is like these 5 steps are done in sequence, and therefore this software emulated cache is almost 5 times slower than the normal memory access to this. Roughly that's what happens in these different steps. So you could do that. What is the point of doing all this? This looks like it's very, very inefficient. From a time point of view, energy point of view, it's also inefficient. But the advantage is that you can create this. This is a software structure. It's a data structure. You can allocate, you can deallocate it. If you don't need it, you could throw all of it out, and the whole thing just becomes a Scratchpad memory. If it turns out that the compiler analysis is hard for a certain part of the code, maybe some particular loops where you know that locality is there, but it is just hard to predict where that data is, then we could say that for that section we will instantiate a software emulated cache which will anyway do better than if I did nothing. Remember, if I am not able to resolve my accesses well in software, in a software managed memory, then all of them would go to the next level of the memory. All of them are going to DRAM. That would be bad anyway. So this intermediate solution might still be better, not as good as just directly reading it from the cache, if it was from the Scratchpad, if it was on this side, but it's of intermediate complexity, but still better than going all the way out to the main memory all the time. Okay. So just wanted to throw open this sort of a possibility. You wouldn't think about it in a general purpose computing architecture, but these alternative ideas are very interesting with respect to optimizing individual applications, certainly. But some of these are in some form or the other, like you see that they have been adopted into GPUs. GPUs, as you know, are not merely doing graphics. They are being used for a lot of general purpose applications also. So there are applications you do need to be careful regarding when to use it and how to use it, but these are powerful tools that are available to us. Okay. So it could be that I have an application go left to right. That's my phase 1, that's my phase 2, that's my phase 3. It could be that there is one phase in which the accesses are all very regular. You can see that I is going from 1 to something. There is an access to I. This is just extracted from one of those spec benchmarks. There could be some other part in which the accesses are not so simple. Like this is similar to that histogram lookup that we did, where you are reading a value and that index is a function of that value. You can't predict that value ahead of time. It could be, so that's these accesses are likely to be irregular. In some other part it is likely to be regular. You could formulate it as a compiler problem where the compiler will make this automatic decision of in each of these regions, how should I access my data? Okay, should I access that array through the cache hierarchy, or should I access it through the Scratchpad hierarchy? You could formulate it as a problem. I will not go into the detail, but you could formulate it as an access graph in which each of these nodes captures some information. It models the effect of mapping an array into a direct memory structure or into the software emulated cache structure. And these edges somehow, these node weights and edge weights somehow capture for us the cost of doing so, cost of mapping it one way or the other. I didn't say how we do that, but it would have to be done in some way. And you could formulate this kind of a problem, for example, a sequential one, into once you have a graph structure of this kind, you are looking for a minimum cost, the shortest path from the start to the end. That if the shortest path is this, it means that you are predicting that it is better to use a Scratchpad structure for the first phase, a cache structure in the second phase, and a Scratchpad structure in the third phase. Just giving an idea of how one might want to model it. Assumption here was that this is all linear, just one bunch of loops and arranged in a linear way, but you could extend that into a more complex control flow graph. The idea is the same, that in each of these, so these are 3 loops that are there, and the relationship is more complex. It's not a linear structure like the previous one, which is very easy to handle, but it could be that you expand each of them into 4 different configurations or n different configurations. If it is possible to partition your local memory structure into cache and Scratchpad in n different ways. Okay, and here we are trying to find out again a similar kind of a formulation, where we are trying to find the minimum configuration, where we pick one from each. Okay, this corresponds to one loop, that corresponds to one loop, these corresponds to the configuration of the memory in each of the loops. So picking one from here, and one from here, and say that that's the desired structure. Okay. So wanted to point this out as some of the possibilities, very interesting possibilities that are involved in this kind of an embedded systems memory management space that involves nice interactions between the architectural possibilities on one side and compiler analysis on the other to make interesting decisions. In the meantime, there are some very interesting things that have happened. There's a sort of an interesting convergence of architectural ideas between the embedded systems domain and the general purpose computing domain. What kind of convergence are these? The embedded systems are actually getting more and more sophisticated. Right? They, even though they started off as very simple systems, they have a large number of processor cores within them. There is on-chip network, there are cache levels. It looks actually no less complicated than any of these server class processors. You look at these general purpose processors, in fact, they are beginning to look more and more like these other guys. They have accelerators within those processors that are very application specific, as opposed to what we have learned in a textbook of what a processor looks like. What he was talking about Power 9, in fact, you recall there are accelerators. Maybe today it is a neural network accelerator or a vision or a cryptography. Many of these applications, if they are sufficiently important, then the architect might want to put some dedicated hardware in the system to accelerate that application. You can see that conceptually there is some convergence. Both of these came from different directions, but they are they're beginning to look similar, and therefore the kind of problems that are addressed also are sort of relevant in both the contexts, for example. Okay, in the time that remains, let me quickly try to go through a co-optimization problem that was defined. This was done with Intel, and therefore the space is a little bit closer to the general purpose space. Nevertheless, the kind of problems that we are looking at, because of the convergence that I'm talking about, because there are these accelerators, there are all these application specific things, some of these ideas are sort of applicable no matter where you stand. Okay. But the point of this part of the presentation is to just point out some, is to discuss some evolution. Some part of the problem is a classical problem, but it is evolved in some ways. But the solution that is being explored is new. It offers some different perspectives to well-known problems. So let's pick up an example architecture that looks like this. These are the different processor cores that have private L1 and L2 structures. There is a network on a chip, and there is a last level cache, and finally there is a DRAM. What are we trying to optimize? We would like to optimize this for both performance and energy in a way that you define a metric that sometimes the one that is used is an energy delay product. Okay, so that if you optimize for energy, your delay should not become too bad. You optimize for delay, your energy should not become too bad. The product of the two could be used as a good metric. What are the energy optimization possibilities? These are known things. There is the dynamic voltage and frequency scaling that can happen in the individual processor cores. There is such a scaling that can happen in that network on the chip. Okay, depending on the kind of traffic that you are seeing, you could make it faster or slower. There is a cache partitioning that could happen in that last level cache. This part of the problem is something that is well known. It is a well studied problem, but the context here was a joint optimization of this, considering that you could change these things. So these are like different knobs that are available to us. I could change things here, I could change things here, I could also do some way partitioning. What is a good way to formulate this problem? How do I address this problem? This has to be dynamically done because applications are changing, application phases are changing, the application behaviors are changing. We have to adapt our solutions as the system is working. It is a runtime solution. So I will omit some of the details, but the problem statement is that you dynamically adapt the system such that these are my controls, right? The core frequencies are available to us. The network frequency is available to us for changing. That LLC can be partitioned in different ways. I want to optimize, let's say, my total EDP is the energy delay product. Just as an intuition, there are other factors that are involved, but you could take some situations. What we have taken here are, let's say, these are the 4 cores. They are running applications, some of which are compute intensive, some of which are memory intensive. This has to be characterized in some way at runtime, but let's say that's what it is. Then it means that perhaps as far as the frequencies are concerned, we will make these as high frequency because they are compute intensive. These ones we could actually make them lower frequency because the bottleneck is the memory. It doesn't necessarily help to run them at high frequencies because you are stalling a number of for a large amount of time anyway. Well, the NOC frequency could be high or low depending on the amount of memory traffic that you are expecting. So if there are a lot of memory oriented, memory intensive applications, then possibly the traffic is high, therefore we might want to use higher NOC frequency. So you could do such a case by case study. The problem is that there are too many cases there. So somehow a runtime system has to be able to adapt this. I could argue similarly that I have so many cache ways, I can, assuming I have the flexibility, decide to allocate some number of ways excuse me, to the first core. So instead of making it equally shareable by all, I could say that part of it is dedicated to one core, part of it is dedicated to some other core, and so on. This has the advantage that one application does not interfere with data of the other application if you were to do this. Knobs like these are already present in modern processors. So anyway, that's the context. The formalism is based on a reinforcement learning idea, where you have a simple Markov decision process consisting of a set of states, a set of actions. This is the general picture. The idea is you have an agent that is our cache controller, or that system controller in this case. It is interacting with the environment. What is the environment? It is the architecture is the environment. It is observing how well it is doing by looking at throughput and EDP and so on. Yeah. 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 Yeah, I didn't. There is a little bit of management that needs to be done. This has to be done in a way that is correct, of course. And if it means that the data was there of one application, and now I have now allocated it to the other core, it means that if there was dirty data, that has to be written back. So some little bit of management has to be done. This isn't that hard though. The overhead isn't really big. It could be that so you have to decide what happens on a read now when there is a transition, what happens on the write when there is a transition. It can be done efficiently. You don't have to write the entire bank for example in order to be consistent. It's all right, the policy. There is a little bit of overhead, but it isn't too much. The mapping function does not change. It is the cache mapping functions are the same. Only thing is now there is dirty data possibly from the other application. What do you do about it? It has to be done. So next time new data is brought in, that would be done, have to be thrown out in a way that does not really affect too much the way the system works. This is done through some simple mask that is available. You say that you design a mask that says that now onwards these two ways are going to be dedicated to this core, these two ways are going to be dedicated to this core, and so on. While that flexibility is not necessarily available to the programmer, our understanding is that modern commercial processors already have this flexibility. Internally they have it. Okay, there is some detail here that I will skip, but the idea is that there is a controller here. I'll have to decide for each of these individual cores. I have to define a controller for that network, and there is a controller, separate controller for the partitioning of the LLC. And while the formalism is a general one, I would have to define in my context what are the states, what are the actions, and what is the reward. That is how that formalism works. Whatever your specific problem is, there is some effort that needs to model that problem in terms of the states so that a reasonable learning can happen. By itself those tools are good, but they are only as good as you are able to map your specific problem into those mechanisms. So I'll skip the detail, but anyway, the point is that you can't have too many states. There is some nice relationship between the complexity of this model that we are building in terms of states and actions and what you can expect with respect to quality, which is really what I wanted to point out. I can skip some of the details here. But let me skip over the mechanisms and comment about some of the interesting challenges that occur in this space. The results are good. I maybe have a slide just summarizing it. The results are nice, but there are some practical difficulties as we try to establish how well this system is working. For example, you have relatively few data points. learning occurs well if you have a large number of data points. If the number of data points is small, then it does not occur well. So even if the system ultimately is going to be implemented at runtime, and you can hope that at that time there is a large amount of data, but in the process of establishing it, we are doing simulations, and the simulations are very slow, and therefore the quality of the results that we observe are in some ways circumscribed by the speed of those simulations. If that were better, if that infrastructure is better, in fact, you might actually have better results, possibly, but we don't know that. If it is implemented on real hardware, you expect that results will be better, but how much better it is, it's hard to say. That state space needs to be tightly controlled. These models are determined by essentially how many states are there, how many actions are there, how dense that structure is of states and actions. And if that state space, if the number of states, for example, increases, number of actions increases, then there is a danger of that space blowing up too much, so much that you are not able to do a good learning. Considering, remember that the number of data points is not large. Of course, that need not be a real limitation, but in an academic setting, often it becomes a limitation. But implementing it is an interesting thing. Where do you implement that algorithm? Whatever that algorithm is, you could implement it in hardware. Separate hardware could be dedicated for just this. It could be that you use one of the processor cores to do this kind of management. That's also okay, because most of the time that machine is not learning, it's just capturing data that is happening independently. Once in a while you would stall the system and take a decision, so there is an overhead, maybe not too much of an overhead. But the interesting thing is, there is an improvement. We didn't go into the experimental results, but the results are good. One of the powerful implications is that there is, if these results are good, then there is no need for a very sophisticated modeling of various effects that are there in the processor, because these are all very non-trivial. It's hard to come up with an exact model, very well behaved model. For example, there are process variation effects. Processor to processor, there are changes because semiconductor processes they are not stable. Right? There will be small differences in the delays. Such an mechanism is immune to that. There is no need to model process variation into a standard model that would be built in a classical way partitioning system, for example. So there are some powerful advantages of such an approach that I would like to maybe conclude with. I've already taken a couple of minutes beyond what was assigned. So that last part was a learning-based architecture optimization. While it was applied to that particular co-optimization problem, you can see that the mechanism is a general one. People are using such kind of approaches to rethink some of the classical architecture optimizations. So what we talked about is a sort of a general framework for incorporating disparate optimization mechanism. Individually, the systems are well studied and well modeled, but when you try to co-optimize across many different things, the space of the exploration space of the optimization increases so much that possibly some of these alternative mechanisms might be interesting. And what's most interesting about this, of course, is that these memory architectures keep changing. It's a very rapidly evolving scenario. Accelerators come in, means they throw in very different kind of traffic into these standard memory hierarchies, and therefore they present some very nice opportunities for exploiting them at various system level, higher level phases. So that's what I would like to conclude the talk with. Thank you.